Let's talk about splitting fields. So here's a definition. Let F be a field and let small f denote a polynomial in the ring f of x. An extension field k of f, so let's denote it in the usual way, k is an extension field of f, is called a splitting field of this polynomial f of x if two conditions are satisfied. So let's write them both out. Number one, this polynomial f of x factors completely into linear factors. So this polynomial should into linear factors in the polynomial ring kx. In other words, I can write fx as a product of x minus alpha 1, alpha 2, alpha 3 and so on till x minus alpha n, and of course if you assume that the polynomial is not monic, that there is some leading coefficient, then that leading coefficient also comes out in front. Okay, so we will typically assume that we are talking about monic polynomials or ones where the leading coefficient is 1. Sorry. So fx is such a product for some elements alpha 1, alpha 2, alpha n in the extension field k, and as I said, here what is n? N is the degree of the polynomial f, and c is just the leading coefficient. So that's in fact an element of the ground field f. Okay, so this is the leading coefficient of f, coefficient of the highest term x power n. This is of course an element of f. Okay, so the condition 1 is really that it should factor completely into linear factors. Okay, in other words, there are n roots for this polynomial in the extension field k. Secondly, this property does not hold for any smaller subfield. Okay, so in some sense k is the smallest. Let's write that out precisely. F of x does not factor completely into linear factors in, let's say, E of x, where for any subfield, what is E? E is a subfield which contains f, but it's a proper subfield. Okay, so this is a proper, so by this I just mean E is a proper subfield of k which contains f. Okay, proper subfield containing f. Okay, so these are the two properties that you need for a field k or an extension k to be called a splitting field. Okay, so now let's give some examples. So here are some easy examples of splitting fields of polynomials. If I take my field to be the rational numbers and my polynomial to be x square plus 1, then the splitting field turns out to be something that we've seen before in the earlier lectures. So this is the field of Gaussian integers, or rather the field of rational numbers with the Gaussian rationals, if you wish. So it's all, so we know what this is. This is a set of all a plus ib, a and b running over the rational numbers. Okay, and why is this field a splitting field in this case? So we need to check the two conditions. So I claim that k is in fact a splitting field. K is a splitting field of this polynomial f, because, well, first property, f should split into linear factors over k, and that's satisfied because this polynomial splits as x minus I into x plus I, and the I that now appears here is after all an element of this field. So you can think of this as the factorization of f of x in the ring k of x, where k is now the field q of I. Okay. Secondly, second property which we need is that this should somehow be the smallest, that this property should not hold for any intermediate subfield or a proper subfield. But recall again from what you've seen before that the extension q of I over q is of degree 2, right? This is a degree 2 extension, which means that you really can't have any subfield. So there exists no subfields E which are strictly between q and qi, right? A strict intermediate subfield doesn't exist, right? Because 2 is really a prime number, and you've seen this property of degrees of extensions are multiplicative, right? So when you have a degree 2 extension, it doesn't admit any subfields. So there can't be E's which are strictly between q and qi, and of course for E equal to q itself, this the polynomial f doesn't split over q. Okay. Also we need to check that q itself is not going to work, and that is clear here. Observe that f does not split completely over q, right? Because what are the two roots plus and minus I? They are not in q, so you cannot factorize it completely into linear factors over q. So what does that mean? This extension k also satisfies the second property that you need, right? The only proper subfield of qi is q itself, and the polynomial f does not split completely over q. Okay, so that proves that k is the splitting field. Note that condition 2 or condition B in the definition can be replaced with an equivalent condition. So let's call that B dashed. Okay, this is now called condition B dash, which is the following, that f of alpha 1, alpha 2, alpha n equals k, where what is f of alpha 1 through alpha n? This is just the subfield of k generated by f and the roots alpha 1 through alpha n of small f. Okay, and it's easy to see that you can replace b with b dash, meaning they are equivalent. For example, if you chose to keep b as your definition, then b dash follows naturally because of the following reason. B says that there are no intermediate subfields, there are no proper subfields over which the polynomial f splits completely. Now if you assume that, then b dash follows because of the following, that f of alpha 1 through alpha n will in fact be a subfield of k over which this is a subfield of k, and the polynomial f certainly splits over this subfield. Okay, so by the hypothesis of B, this cannot happen unless this subfield is the whole field. Okay. Now similarly, if you chose to keep B dashed as your definition, then B follows, as we will see in just a second. So let's proceed by contradiction. Suppose B is false, suppose not. Okay. So what does that mean? Say there exists an intermediate subfield. So let's say E, which is a proper subfield of K, and E containing F, such that F splits over E. Okay. Now what does f splitting over E mean? Well, it just says the following, that you can write f of x. Okay. So let me ignore the leading coefficient of f. I'm just going to assume its the leading coefficient is 1, that it is a monic polynomial. So let me write f as the product of x minus beta i's coming from the intermediate subfield, and this is of course because we have assumed now that f splits over E. Okay. Now observe that this is, on the other hand, we also know that x is the product of x minus alpha i's, and now the alpha i's are coming from the ambient field K. Okay. Now these two different factorizations, so these are both factorizations, you can think of these both as factorizations of f in the ring K of x, right? Because E is after all a sub of K, I can think of the first expression also as being a factorization over K of x. So now I have two different factorizations in the ring K of x, but that's K of x is a unique factorization domain, and each of these x minus alpha i's or x minus beta i's, they are all just linear polynomials, so they are definitely irreducible polynomials. And if you have two different factorizations, then that, you know, the only possibility is that they really coincide with each other. Okay. So K of x is a UFD, unique factorization domain, and all the terms here are just linear, x minus alpha, x minus beta I, etc. are definitely irreducible polynomials. Okay, so what does that mean? This means that these two factorizations are the same. In other words, if I take, well, alpha I 1 to n, well, there are potentially repetitions here. So let me call this the multi-set. Okay, by which I mean you also keep track of how many times each alpha I appears. The multi-set of alpha i's must coincide with the multi-set of beta i's. Okay, in particular, what does that mean? This means that all the roots are actually in the smaller subfield inside E, right? Because each alpha I is the same as some beta j, and the betas of course are in E, right? So all the alphas are in E, and what does that mean? It means that the subfield generated by f and the alphas is also contained in E, right? Because f is of course already in E and all the alphas are now in E according to this. But what does that mean? Well, we assumed according to B dashed that K is the same as this subfield. So we conclude that K is a sub of E. Okay, and that's no a contradiction, because to begin with K was or rather E was a proper subfield of K. Okay, so this is just to say that, you know, sometimes it's more convenient to use this characterization B dash rather than B itself, but they are really the same thing. Okay, so let's move on. So here's our main theorem in some sense, one of our main theorems, and this really says that every polynomial has a splitting field. So every polynomial has a splitting field. Okay, that's in words, but let me make that a bit more formal. So let f be a field and let f of x be a polynomial, and there exists an extension K of f which is a splitting field of f. Okay, I mean, I could have just said there exists K which is a splitting field of f, because being an extension is of course part of the definition. Okay, but I'll just state it for more clarity. So here's the proof. How does one construct a splitting field? Okay, so well, we need to remember to do two things. One, we need to find a field over which f splits completely into linear factors, and that field is, well, one such field is definitely already available to us, something that you have seen before, and this is the algebraic closure. Okay, so let's begin with that as our first approximation. Let f bar be the algebraic closure of the field f. So recall that such a thing exists. So what's the algebraic closure? It's an extension of f which has two properties. Number one, that this extension is an algebraic extension, and f bar is algebraically closed. Okay, which means that any polynomial with coefficients in f bar will have all its roots in f bar. Okay, the example, classic example being the field of complex numbers itself. Okay, and f bar algebraically closed. That's the definition of the algebraic closure. And recall the two main facts, that given any field f, there exists an algebraic closure, and it is essentially unique. Okay, and by essentially I mean abstractly there could be many algebraic closures, but any two algebraic closures are isomorphic to each other by an isomorphism which is identity on the field f. Okay, so this is, recall this from what you have seen before. Now f bar already gives us a first approximation to what we want, to a splitting field. So let's just take this polynomial f. We know for sure it splits over f bar. So we can write it as a product of linear factors alpha I equals 1 to n, where alpha i's come from the algebraic closure. Okay. Now define the splitting field then. Remember, we have our property b dash, so it sort of tells us what we should do in order to construct the splitting field. Inside the algebraic closure, you just take the subfield which is generated by f and these n roots of this polynomial small f. Okay, so we have a candidate now which is inside the chosen algebraic closure, and now it's just a question of checking the properties. Claim k is a splitting field of this polynomial fx. Proof, well, number one, it's obvious that f splits over k. Splits completely over k is clear because well, this expression here that we wrote out, this star holds. I mean, it splits completely. Now the point is that the alpha i's that we have, they are by definition elements of k. Okay, since the alpha i's are all elements of k. Okay, so that's the first property. And secondly, let's check axiom b dashed instead of b. Well, because that's really how we constructed k. And so observe that k is by definition the subfield of itself, which is generated by f and the alpha 1 through alpha n. Okay, so this is more or less by definition. Okay, it follows quickly from the way we defined it. Okay, so which implies that we have checked the axioms a and the axiom b dashed hold, and so we are done. So that proves that k is a splitting field. Okay, now analogous to what I just said about algebraic closures, that not just do they exist, but they are unique, meaning essentially unique. There exists a isomorphism between any two algebraic closures which restricts to an identity on f. Now we will show the same result is true for splitting fields as well. Okay, if you fix a polynomial small f, the splitting field is essentially unique. There is really only one splitting field up to an isomorphism which is identity on the base field. Okay, but before we do that, let's prove some other simpler properties of the splitting field. So we observe before proving the uniqueness that the splitting field is necessarily a finite extension. splitting field of the polynomial fx is or must be a finite extension of the field f. Okay. In fact, here's a more quantitative proposition. It says let f be a polynomial and k be its splitting field, a splitting field, we still haven't shown uniqueness, be a splitting field of f, then not only is k a finite extension of f, we also have a bound on the degree of the extension. Okay, it's finite and the degree is at most n factorial. Okay, so let's prove this. Proof is rather easy. Okay, now what do we know? We know that k is a splitting field. So let's write out the roots. Let alpha 1 to alpha n in k be the roots of this polynomial f in the field k. We know the following. We know that k is just f of alpha 1, alpha 2, alpha n. Okay, so let's sort of go in stages. So let's take the very first one of the alphas. So consider alpha 1. So let's say look at just the first fellow, alpha 1 alone, and look at the extension. So adjoin alpha 1 to f and look at the field f adjoined alpha 1. Think of it as an extension of f. Okay, so in some sense all of this is really inside k, so I should probably just say this is really a subfield of k as well. Now let's do the following. So we will eventually show k is finite by building it up as a tower of extensions. Okay, so let's look at this very first guy, f alpha 1 over f. So let m1 of x in f of x, okay, denote the minimal polynomial, okay, by which I mean the minimal degree irreducible polynomial satisfied by alpha 1, denote the minimal polynomial of alpha 1 over the field f. Okay, so I can also assume it is monic. So what is m1x? Recall, this just means m1x is the minimal degree monic polynomial in fx satisfied by alpha, such that m1 of alpha 1 is c. Now since f of alpha 1 is 0, what this means is that m1 must divide f, right, because a minimal polynomial certainly divides any other polynomial which annihilates alpha 1. So in particular this means that the degree of m1 is at most the degree of f. Okay, and the degree of f is what I am calling n, by the way. So I should probably have said that in the definition, where n equals the degree of the polynomial f. Okay, so at the very first step, the first extension has degree that's at most n. So that's the first observation. This degree is at the most n. Okay, now let's see where we are. Where does this leave us? We have at least gotten one of the roots in play, f of alpha 1 over f, but when I construct this extension f alpha 1, many of the other roots, alpha 2, alpha 3, some number of the other roots may already be part of this extension. Okay, for example, maybe alpha 2 is equal to alpha 1, or maybe alpha 2 is minus alpha 1, or some polynomial in alpha 1, say alpha 1 square plus 2 alpha 1 plus 3 or something like that. So some number of the other roots may already be part of this extension f alpha 1. Okay. Now if all the other roots are part of f alpha 1, then you are done, because f alpha 1 itself is the full extension k. But suppose not. Okay. So let's write out what I just said. So sum of the other alpha i's may already belong to f alpha 1. Okay. Now if all of them belong, then you are done. If all the other alpha I belong to this extension, then that just means that k is just f alpha 1 itself, because k, remember, is f of alpha 1, alpha 2, alpha n. Okay, and we are done. Why are we done? Because we have shown that the extension size is at most n, and n is definitely smaller than or equal to n factorial. Now if not, suppose if not, at least one of the other alphas is not part of f alpha 1. Let's say alpha 2 is not part of f alpha 1. Say alpha 2 doesn't belong to the extension f alpha 1. Then we sort of repeat the argument. So let m2 now denote be the minimal polynomial, we'll abbreviate it to min poly, of alpha 2 over the extension f alpha 1. Okay. So then again, by the same reasoning as before, m2 is a min poly for alpha 2, f is a polynomial which f such that f alpha 2 is 0. So m2 must divide f. Okay. But what is f now? So let's just look at f of x. F of x looks like this. We know for sure that alpha 1 is the first root that we wrote out. So it's x minus alpha 1 into some polynomial p of x. So let me factorize f like this: x minus alpha 1 into p of x, where p of x is a polynomial with coefficients in the field f alpha 1. Okay. So of course when you go to k, p of x will be the product of the other factors, x minus alpha 2, alpha 3 and so on. But because alpha 1 belongs to the field f alpha 1, I can pull out that factor alone and think of the remaining factors as being some polynomial in f alpha 1 of x. Okay. So m2, this polynomial m2 of x, must divide x minus alpha 1 into p of x. Okay. So this is just the factorization in this polynomial ring. Okay, but now observe that m2 is an irreducible polynomial because it's a minimal polynomial. Okay, in this ring f of alpha 1 of x. Okay, and this first factor, so here is an irreducible polynomial which divides a product of two polynomials, x minus alpha 1 into px. Okay, so clearly m2 of x does not divide the first factor, right? Because, well, the first factor is just a linear factor. So observe m2 cannot divide the first factor. In fact, it's relatively prime to the first factor, because you can just think of this as being an irreducible polynomial of degree 1 in this field f alpha 1 of x, in this ring f alpha 1 of x. Okay, so now what does this mean again? I mean, you can think in terms of the fact that m2 of x is a prime element of the ring f alpha 1 of x, or in terms of the unique factorization, the fact that this is a UFD and so on. So the point is these two are relatively prime to each other. So therefore m2 of x has to divide the other term, which is p of x. Okay. So what does that mean? That means that the degree of m2 is at most the degree of p, and the degree of p is at most n minus 1, because the factor x minus alpha 1 has already been pulled out of f. What's remaining is of degree at most n minus 1. Okay, so what does this mean? This tells you then that when you look at the extension, so I had f alpha 1 and now I adjoin another element alpha 2 to it to form a further extension. This new extension that I have formed has degree at most n minus 1, because it's at most the degree of p. Okay, and this we had already seen has degree at most n. Okay, so this means f of, so by the way, f alpha 1 adjoined alpha 2 is just what we call f adjoined alpha 1 alpha 2. I mean, it's the same thing really. So this degree is at most n minus 1. Okay, and now it's clear what we need to do. If you repeat the same argument, repeating the argument, maybe some of the other alphas are now already part of f alpha 1 alpha 2, but if not, you can adjoin that additional alpha, and the minimal polynomial of the new alpha that you adjoin will be at most n minus 2. Okay, for the same reason, because you now pull out both x minus alpha 1 and x minus alpha 2. Okay, so repeating the argument, here's what we conclude. We conclude that we must reach K, which is the entire splitting field, in at most n steps. Okay, because you can adjoin one at each step, and you may not need n steps. In some of the intermediate steps, some of the other alphas may automatically be part of this. Okay, so but the worst case is that you need n steps, and at each step the degree that you get is n, at most n minus 1, at most n minus 2, and so on. So the product of the degrees involved therefore is degrees of the intermediate extensions is at most n into n minus 1, and so on till 1, which is n factorial. Okay, so that's the end of the proof. Okay, in fact, thing to note here, remark, is that we actually have also seen, I mean, in the course of the proof, sort of a way to construct the splitting field, if you will. Okay, so remark, this also gives us a constructive way of, this also gives us a construction of f of k, the splitting field. Okay, what you do at each step, you adjoin one at a time, and then you know, you see how many of the other roots still haven't fallen into the extension at that point, and then you adjoin that root. Okay, so for example, if I took the field f to be q and my polynomial f of x to be x cubed minus 2, which we know factorizes like this, x minus cube root 2, x minus cube root of 2 omega and omega square. So these are the complex numbers, where omega is the cube root of unity. So let's write it as minus 1 plus root 3i by 2. Okay, this is the cube root of unity. Then here's what we can do to construct the splitting field step by step, in some sense, which is that you first adjoin the first root. So I can say, okay, I have q of cube root 2. Now at this stage, what I find is that the other two roots, which are cube root of 2 omega and cube root of 2 omega square, they are complex. They have a non-zero imaginary part, and they are not part of this extension at this point, right? Q of cube root of 2 is certainly part of the real numbers. There are no, everything here has imaginary part 0. Okay, now what we can do is say, okay, fine, I have two more left, so let me adjoin one of them. So I can try and adjoin, let's push this down. So I look at now adjoining cube root of 2 with cube root of 2 omega. Okay, now the point is, when I adjoin this additional guy, then turns out that the third fellow is automatically part of this extension. Okay, Why is that? So let's just give these fellows names again. Cube root of 2 is alpha 1, this is alpha 2, and let's say this is the third root alpha 3. Observe that how do I get alpha 3? Alpha 3 is just nothing but alpha 2 square divided by alpha 1. Okay, so that's exactly the relationship among these three. So that just means that alpha 3 is actually some polynomial combination of well, I mean it's in the field, so I'm also allowed to divide if you wish. So it's some combination of alpha 1 and alpha 2 here. Okay, so this is certainly in the field generated by, so this is over Q, it's in the field generated by alpha 1 and alpha 2. Okay, so you don't need to do one further step of extension here. You won't need to go one more step. Okay, so this is sort of a constructive way of just understanding what splitting fields are. And in this case, so this is the thing that we obtain at the end here. Let's call that K. Let's call that K here. So this K is in fact the splitting field. So claim K is exactly the splitting field. K is the splitting field of, well, it's a splitting field of this polynomial fx. Okay, so it's clear that it is a splitting field because number one, it splits, the polynomial splits over this field certainly, and the roots of this polynomial generate this field K more or less by definition. In fact, the first two roots are enough to generate the whole thing. So that's easy, but the second part of the claim is that here KQ is in fact, well, it's actually 6. Okay, so we claim that in this case the degree of this extension is 6, and that's something that one needs to verify. It requires a little proof, so let's just do that quickly. So I claim that this very first extension has degree 3 and the thing on top has degree 2. Okay, so we just need to verify these two things, and that will show that it is 6. So why does the first extension have degree 3? Because if I take this polynomial f of x equals x cube minus 2, so here are some facts. This is actually irreducible over q. This is an irreducible polynomial. So that's fact 1. Okay, why is this irreducible over q? Well, it's a cubic polynomial. If it were not irreducible, then it would factor into, there will be at least two factors. You will have to write it as sum a of x into b of x. Okay, so I'm just giving you a quick proof of why it's irreducible. If not, f can be written as a product ax bx, and since the total degree is 3, at least one of them is a linear polynomial. Okay, one of them has to be degree 1, the other is degree 2. So what does this mean? This means that a of x, therefore let me assume a of x is a linear polynomial. It look like some x minus some gamma, okay, where gamma is a element of q. Okay, in other words, there is a root gamma. In other words, gamma is a root of this polynomial. So which means then that f of gamma is actually 0, right? Because a of gamma is 0, and so f gamma is 0. So a cubic polynomial, which is, if it's not irreducible over q, it must have a root in q. Okay, and one can easily check that none of these three fellows is in q, right? I mean, it's clear that this is irrational. Maybe one has to give a short proof of that, but since cube root of 2 is irrational, it's not in q, and these two are clearly not in q, right? They have some imaginary part. So you can't have any of the roots be in q, which means that this polynomial must be reducible over q. So that shows that the first element you adjoin, which is cube root of 2, its minimal polynomial has degree 3. Its minimal polynomial is exactly this. Therefore, by what you have seen before, when you adjoin a single element, the degree of the extension is just the degree of its minimal polynomial. So that's degree 3. Now for the second guy, we need to check that it's a degree 2 extension, and again there it's just a question of figuring out what the minimal polynomial looks like. So observe x cube minus 2 is can be factorized as follows: x minus 2 into x squared plus cube root of 2x plus cube root of 2 the whole square. Okay, so this is just the factorization, and this is a factorization with coefficients coming from the field cube root of 2. Okay, now this polynomial here, so this polynomial, so let's call it p of x. So observe, p of x is an irreducible quadratic polynomial. So it is irreducible over this field cube root of 2. Okay, again, why? Same reason. If it is reducible, then it must have a root in the field cube root of 2. Okay, so again, reason, if not, then there exists a root of p in this field cube root of 2. Okay, but clearly that can't happen, because the roots of p are the other two roots, cube root of 2 omega and omega square, and they are, they all have imaginary parts. So the other two roots clearly don't belong to this subfield cube root 2. Okay, so that's clearly false. Okay, so what that means again is, if I take this cube root 2 and I adjoin this additional element cube root of 2 omega to it, right, this cube root of 2 omega satisfies the polynomial p, and that polynomial has degree 2 and it is irreducible. That means that the degree of the extension is also the same as the degree of its minimal polynomial. Okay, so this means that p is exactly the minimal polynomial of cube root of 2 omega over the field q of cube root of 2. Okay, so the degree of the extension is 2, and well, that's all we needed to prove, that the total extension has degree 6. So we are done.